Dimensional analysis practice. In this video, you can practice using dimensional analysis and see the power of it applied to something like a real exam situation. As part of an examination a few years ago, a student went through the algebraic manipulation shown in the box to the right. So that's here. At this point, there's just a lot of letters in there. You don't necessarily know what those symbols mean. But the cool thing is, even without knowing what the symbols mean, if you're given the information about their dimensions, which is here at the right, you can answer some questions. And the questions we want to answer here are A, is it possible that the final equation the student got here on their exam is correct? If the final equation is not correct, does that mean the starting equation, the one up here, is wrong? And then if the final equation is not correct and the starting equation is not wrong, can you find the error using dimensional analysis? So the really cool thing is this shows how you can use dimensional analysis to check yourself on an exam and really even finally pinpoint where the error might be. All right, so let's start with A. Is it possible that the final equation is correct? Now here, what we want to do is decide if this equation here is correct using dimensional analysis. So like any problem we do in this course, we can use the ACE-M problem-solving strategy, problem-solving framework to think about this. And the first part of that is to analyze the task, which means understand the problem and identify the goals and what's known and unknown. And then the next part would be to create a plan. So why don't you take a minute here to pause this video and see if you can analyze the task and create the plan before we go on to the next part. All right, so in my analysis, when I'm analyzing this, one of the nice things about me telling you it's dimensional analysis practice is you can already sort of understand the problem, right? So what we're trying to do is figure out if the dimensions in this final equation work. And in dimensional analysis, in class, I've mentioned that there's two ways to use dimensional analysis. One is to check if equations are correct, and the other is to figure out what the dimensions are of a variable when you using an equation. So this is clearly the first one. We're using it to check if an equation is correct. Right. And then we know that when we're doing this, there's a few aspects of the dimensions that we want to think about. First is dimensions on the two sides of an equal sign must be the same. And the next is that you can only add or subtract things that have the same dimensions. All right, so now that I have done my analysis, the next thing is to create a plan. And so given my analysis, I think what the plan is going to be is to check these two parts of the equation that are added together and see if those have the same dimensions, since we can only add or subtract things with the same dimensions. And then if these two do have the same dimensions, what I'll then do is check that this term, the GH on the left, has the same dimensions as the right-hand side. And the way I'll figure out the dimensions is using this list along here to get the dimensions of each term in the equation. All right, so that's the plan. Get the dimensions of each term in the equation. All right, I'm going to start with the dimensions of a half v squared. This bracket here that I'm drawing means dimensions of. So a half is a number. It doesn't have any dimensions. And if we look over here, we can see that v has the dimensions of length over time. So this equals length over time, but then because v is squared, its dimensions are also squared. So the dimensions of a half v squared would be length over time squared, and then if I wanted to write it all out, I could distribute the squared and I would get length squared over time squared. Good, so I'm done with the dimensions of that half v squared. Now what I want to do is to get the dimensions of the half v to the fourth. So this is almost the same. The only thing that's different is that the v is taken to the fourth power, so I have length over time, the dimensions of v, but then taken to the fourth power, which would be L to the fourth over t to the fourth. Now these two are definitely not the same dimensions, right? Length squared over time squared, that'd be meter squared per second squared, for instance. Not the same thing as length to the fourth over time to the fourth, something like meters to the fourth over seconds to the fourth. So we definitely have a problem here. And to answer part A, we'd be done, right? It is not possible that the final equation is correct. But since I know that I'm going to be going on to figure out where exactly the problem is, it might be nice to know which one, the half b squared or the half b to the fourth, is the one that doesn't match the other side of the equal sign. Because remember, these two are breaking the rule that you can only add or subtract things with the same dimensions, but we should also make sure that we're complying with the rule that dimensions have to be the same on the two sides of an equal sign. So to do that, I should get the dimensions of the GH. And to do that, we would look and see over here that G, its dimensions are length over time squared, so something like meters per second squared. So that would be length over time squared. And the dimensions of H are a length. So if we multiply this out with a little algebra, then we get L squared over T squared. And so we can see that that matches the half v squared, so it's this v to the fourth one that's actually wrong. These two match, this one doesn't match dimensionally, so that half v to the fourth is wrong. All right, and we finished part A. Is it possible that the final equation is correct? And the answer is no. All right, so now let's move on to part B. If the final equation is not correct, does that mean that the starting equation is necessarily wrong? All right, so this would be a good place for you to pause again and do the analysis and planning of for this problem. All right, so when I went through and did my analysis and planning for part B, which is where we are now, it's really very similar to part A, right? Again, we're going to be using dimensional analysis to check an equation, and again, the plan should be to get the dimensions of each term in the equation and make sure that they all match each other. So this time, why don't you take a chance, pause the video, and go ahead and try to do the execution of the plan on your own. So try to do this, get the dimensions of each term in the equation. So hopefully after part A, part B wasn't so bad for you to do on your own, but I'll do it here just in case. So this time I'm just going to go through and do each of the terms in this first equation in order, check the dimensions of each one, and see if they match. So the first one is MGH, all multiplied by each other. And we want to get the dimensions of that, so we just multiply the dimensions of each of the three things, M, G, and H. So M has dimensions of mass, which is funny because it just looks like itself. G we've already worked with, has length divided by time squared, and H we've also already worked with, it just has a length. So then what that gives us is when we multiply it all out, we get a mass, a length squared in the numerator, and denominator times squared. And so we have the units of the term on the left-hand side are mass times length squared over time squared. So this could be like kilograms meters squared per second squared. All right, let's do the next one. A half mv squared. And remember, a half doesn't have any units, so it doesn't come over when we're thinking about the dimensional analysis. The m, we already know, has units of mass, and v has units of length over time, and v is squared, so its dimensions are also squared. So when we multiply this out, the dimensions of that term are mass, length squared, over time squared. So far so good. Everything is matching. And let's just do that last term. A half I w squared. We'll learn later in the semester that this particular w is called an omega, but you don't need to know that for now. Again, the half doesn't have any dimensions. I we haven't seen before, and its dimensions, if we go look over here, are a mass times a length squared. And then omega, the W, its dimensions are 1 over time, so like 1 over seconds, for instance. And then omega is squared, so its dimensions get squared. And then when we multiply it all out, we get a mass and a length squared over time squared. And here, everything is consistent. So up here, every term has the same dimensions. So while we're not positive that this is a correct equation, it at least means that it is not necessarily wrong. There's nothing inconsistent in the dimensions of this. So we started with something that could be right up here. We ended with something that is wrong up here. So we now have the answer to part B. If the final equation is not correct, does that mean that the starting equation is necessarily wrong? This is another no, right? That starting equation is not necessarily wrong. So that leads to part C. If the final equation is not correct and the starting equation is not wrong, so these are both the things that we've come to conclude in parts A and B, can you find the error using dimensional analysis? All right, so here's the challenge. Can we pinpoint where the student made the error in this exam using dimensional analysis? So this is something you could do on your own exams. If you found that you got a dimensionally inconsistent answer, you could go back through and troubleshoot your work. All right, so why don't you take a minute to do the analysis and planning for this problem. Okay, when I did my analysis and planning, the analysis is the same. This is really the same type of problem, a dimensional analysis problem, and I'm going to be using the same tools. But here my plan is a little different because when I take a look at what's going on here, I see between the first equation and the second equation, most of the things are the same, right? MGH doesn't change, half MV squared doesn't change. The only thing that changes here is instead of I, it seems like this student has substituted MR squared. So really all I need to do to check that this step is all right is check the I that, so in substituting, the student clearly thinks I equals MR squared. And so if they're equal, they should have the same dimensions. And so really my plan only has to be to check that I and MR squared have the same dimensions. And similarly, when the student went from the second equation to the third equation, the only thing that changed is they substituted for the W, the omega, a V squared over R. So I really only have to check these two substitutions to make sure that the dimensions match in the substitutions. All right, so let's do the first one where the substitution is that I was replaced with MR squared. And so this is a question mark here because what we want to do is check that that is consistent with dimensions. You know, we might not know that's 100% correct, but we could at least prove it was wrong if the dimensions were wrong. So to do that, we need to check the dimensions of I and MR squared and see if they match across the equal sign. So the dimensions of I, that's very easy. That's just listed in the table to the right. ML squared. And then the dimensions of MR squared. Oh, this is looking good already. Maybe you can see ahead like I can. MR squared. M has dimensions of M. R has dimensions of length. And since R is squared, its dimensions are also squared. And so we can see that those do in fact. So that substitution between the first and second equation seems to be okay. So let's check the next substitution between the second and third equation. And what happened in this substitution is the student substituted omega squared, the W squared, and they said that that was equal to V squared over R squared. So let's check the dimensions here. So the dimensions of the W, which we'll find out later is called omega, the dimensions of omega squared, well, the dimensions of omega is 1 over time. And then we square that whole thing to get its dimensions 1 over time squared. Now we also need the dimensions of V squared over R squared. This looks a little complicated the way it is, so I'm going to simplify it. So I simplified that here by just taking the squared and distributing it. So V squared squared is V to the fourth. R and the denominator squared, r squared, turns into r squared here. And then I just need to get the dimensions of each of these. V is length over time, and that is to the fourth. And I don't think we've come across this where something's been in the denominator before. So the units of r are length, but it's in the denominator. So I have to put its units in the denominator of a fraction. And then the whole thing is squared. So then we have the units of the whole thing are length to the fourth, or time to the fourth, from the v to the fourth, and then 1 over length squared from our 1 over r squared. And then when we put that all together, some of the lengths cancel, and we get length squared over time to the fourth. And if we check, what we're wanting is that the units of omega squared match the units of the v squared over r squared. And omega squared is 1 over time squared. Ooh. And over here, we've got something like length squared over time to the fourth. So these definitely don't match. Right, we've got an extra factor of L squared on the numerator, and we've got an extra factor of t squared on the numerator. And so that actually looks like maybe if we just hadn't squared our velocity, we might have been okay. All right, so here in part C, we have indeed found the error, and if we wanted to circle it, it would be this step here that was the problem. All right, now you'll notice so far I haven't done the last step of the ACE-M process, the monitoring. And that is partially because really dimensional analysis is the whole process that we've been doing here of dimensional analysis is really part of monitoring, right? The person here has already done their work, and what we're doing is basically a monitoring step for them, checking that everything is all right. So using this dimensional analysis could be part of your regular monitoring of your own problem solving.